Hello, everyone. So last time I introduced the CPM, the critical path method. The CPM is a network-based optimization method, specially designed to help when we conduct planning and scheduling a project. So today we are going to continue to talk about the CPM, and I'm going to give you couple of example problems for today. So first, let me share my screen. Okay. This is the one. Okay. So last time I mentioned that there are two types of network models for a project scheduling, right? They are AOA, activity on arc or activity on arrow model, and activity on node model, activity AON model, which is. So given a list of activities and their predecessors, and I didn't include the duration of each activity in this small example, but usually also include the duration of each activities. If we draw a network diagram, then for this simple example, the AOA model would be like this, and the AON model would be like this. So in the AOA, activity on arc network, the activities are represented by the directed arcs or arrows, and the nodes are used to represent the completion of a set of activities, right? And the activity on node model, the activities are represented by nodes here. Okay, and the goal is to obtain the shortest time required for the completion of the project. Okay, and like it says here in this screen, if the duration of each activity is known with certainty, then the CPM, critical path method, can be used to determine the total length of time required to complete the project. Okay. On the other hand, if the duration of activities is not known with certainty, then the program evaluation or project evaluation and review technique, or PERT, can be used to estimate the probability that the project will be completed by a given deadline. Okay. Okay, and last time we've also discussed these general rules for constructing the AOA network diagram, right? Network model. So given a list of activities and predecessors, the AOA representation of a project can be constructed using these three different rules, okay? Okay, and last time we've considered this example, right? And of course, this the network diagram is wrong because it violates the rule number 3 from this previous screen, that the two nodes can be connected by at most one arc. Okay, but here you can see that nodes number 1 and 2. No, actually, the node number 2 and 3 are connected by more than one arc, right? In this case. So that is the violation of the last rule, rule number 3. So in this case, what you need is to introduce or utilize a dummy activity that takes 0 times, of course. And by using the dummy activity, so in this case, indicated by a dashed line here, dashed arc, right? We may represent the fact that activities A and B are both predecessors of activity C, and it also ensures that activity C cannot begin until both activities A and B are completed. But it does not violate the rule that two nodes can be connected by at most one arc, okay? Okay. And this network diagram also violates the second rule, I believe, because the activity B is also represented by two different arcs in this diagram, right? So according to the rule number 2, any activity on the network diagram should not be represented by more than one arc, okay? So again, utilizing a dummy activity, the given restriction can be represented correctly like this. So here, none of the activities are represented by more than one arc, right? So this is the correct network diagram representation, okay? And last time, we've also learned that there are two key building blocks in CPM, and they are the concept of earliest time, early event time, or ET, or the late event time, or LT, for any event, okay? And we also talked about earliest start time, earliest finish time, and the latest finish time and latest start time, okay? Okay, so to find the early event time for each node in the project network, we use a forward computing method, right? So first we set the early event time for the start node. Usually the node 0 represents the start of the project. So we set the early event time for start node, which is node 0, equal to 0, and then work forward until we determine the early event time for the finish node, right? And we also considered this segment of a project network. So here we assume that we have already know the earliest time for the events numbers 3, 4, and 5. And then we'd like to determine the earliest time for event number 6, right? So we observed that the earliest time for the event number 6 is when all of these 3 activities, A, B, and C, have been completed, right? So we take the maximum value here among these 3 different values, right? So as a result, the earliest time for event number 6 becomes 14, okay? So I decided the earliest time for the final node should be the length of the longest path in the project network from the start node to finish node. Okay? Because when you compute the early event time, earliest time, you always go with the maximum value. Like this, okay? Okay, and the latest time or the late event time is represented by LT. And to find the latest time for each node in the project network, we begin with the finish node, okay? And work backward in descending numerical order until we determine the latest time for the start node, okay? So like it says, for example, if the project can be completed in 38 days, then the latest time for the final node, for the finish node, automatically becomes 38, okay? And then we start the backward computation from the finish node. Okay, so the to illustrate how the latest time is computed, other than the finish node, we used this example last time, right? Given the latest finish time for event number 5, 6, and 7 are given as 11:24 a.m., 11:26 a.m., and 11:28 a.m., okay? And if the 3 minutes and 4 minutes and 5 minutes are required to conduct activities, the A, B, and C, respectively, then we'd like to know what would be the latest finish time for event number 7, event number 4 here, okay? So that's the question. So the event number 4 here can occur after 11:21 a.m., right? Which is from the latest finish time for event number 5, which is 11:24 a.m. minus 3 minutes, right? That is the duration for activity A, right? So if event number 4 occurs after 11:21 a.m., then the event number 5 will occur after 11:24 a.m., right? And in that case, the completion of the project will be delayed. So similarly, if the event number 4 occurs after 11:22 a.m., so in this case, right? Then the completion time of the project will be also delayed, okay? So the latest time for event number 4 can occur has to be 11:21 a.m., okay? Which is the smallest value among these 3 different options, okay? So the latest time for event number 4 becomes 21, okay? Which is equal to 11:21 a.m. So that's the behind the logic why we choose the smallest value when we compute the late event time, okay? Okay, and last time we also talked about the total float, the concept of the total float for each activity, okay? And the total float is the amount by which the duration of activity can be increased without delaying the completion of the project, okay? And the total float can be computed simply by taking the difference between the latest start time and the earliest start time for each activity, okay? Okay, so so as it shows on the screen, if an activity has a zero value for the total float, then any delay in the start of that activity will also delay the completion of the entire project, right? So such an activity is really critical to the completion of the project on time. So that's why any activity with a total float of zero values is called a critical activity, okay? And also a path from the start node to the finish node that consists entirely of critical activities is called a critical path, okay? Okay, so these were what we discussed last time, right? And now let's consider another simple example, okay? So here, a list of activities and their predecessors and the duration of each activity is given in this table, right? And we'd like to know the shortest path, the shortest time required for the whole project. So so we can answer for this using the critical path method that we just discussed, right? Okay, then let me use screen or Word file, or maybe I can use this computer screen then with Excel file. Let me take off my camera. Okay. So, okay. One is AON. Oh, okay. Okay, then before we work on the activity on ARC network, AOA network, let's build up an activity on node network, okay, AON network first. So if you remember, in activity on network on node network, activities are represented by nodes, and the directed arcs are used to represent the completion of a set of activities. Okay. Okay. So actually, the building of the AON network is really easy because the AON network does not require any dummy activities other than beginning and ending node. Okay, so here I'm going to start with here. So this is our start node. And then let's say we are going to have the end node here. Okay. So these two are the only dummy activities, okay, are required for any, sorry, okay, I'm talking about the AON network, okay. For AON network, start and ending nodes are the only dummy activities required for building up the AON network, okay. And here, both activities A and C has no predecessors, right? So we have activity A is down here. And then up here, we have activity C. And both has no predecessor, right? So it has a direct connection from the start node. And then the activity B has A as a predecessor. So I'm going to put B down here. And then directed arc here. Okay. And activity D has one predecessor, which is B. So I'm going to have D here. And then directed arc. Okay. And then activity E actually has two predecessors. They are B and C. So we have B down here and C up here, right? So we have only, okay, we have activity E and also coming from B, right? Like this. And then activity F has one predecessor, which is D. So I'm going to put F down here. And G has one predecessor, which is D. So I'm going to have G up here. And H has one predecessor, which is E. So I'm going to have H up here. And I has one predecessor, which is A. So I'm going to have I down here. And then we have a directed arc coming from activity A. Finally, activity J has three predecessors, F, G, H. So we have F, G, and H. Okay, so I'm going to have J here, right? And then we have directed arc from three activities, three nodes, F, G, H, right? Okay, and that's it, right? But just make sure you're gonna have a connection to the end node, okay? So make sure this end node, that is the event showing the completion, okay? So actually, that's the completion of the entire project, okay? So this is the AON network, which is very easy. Now let's move on to AOA network. So let me delete this. So I'm going to use blue color. Okay. And AOA network. So if you recall, in AOA network, activities are represented by directed arc. Okay. So nodes in the AOA network are also called as the event because it does represent the completion of a set of activities in the AOA network. Okay. Okay, so And in the AOA network, usually node number 0 represents the start of the project. So an arc should lead from this node number 0, to each activity that has no predecessors, because two activities, A and C, has no predecessors, right? So we're going to have directed arc represents activity A, and another one representing activity C, like this, okay? Okay, now activity B has a predecessor, which is A, right? So I'm going to have like this. This is going to be B, okay? And D has one predecessor, which is B. So if I have D, something like that, that should be okay, right? And how about next? E has two predecessors, B and C. So actually, if we draw C here, and we have E down here, and we're going to delete this. What happened here then? Is that correct diagram? So we can see that. So from this diagram, E has two predecessors, B and C, right? So we have E up here has two predecessors, B and C, right? That is correct. But the problem is the D has only one predecessor, which is B. But according to this diagram, the D has also two predecessors, B and C. So this is not the correct diagram, right? So in this case, we need to introduce dummy activity, okay? Utilize that. So instead of moving this C and having the activity E up here, what I'm going to do is introduce dummy activity expressed by dashed arc up here, okay? And then we still have activity C up here. After that, we're going to have activity E up here, okay? So with this diagram, network diagram, activity E has two predecessors. They are B and C, right? However, D has only one predecessor. This is D, and the predecessor is activity B down here, okay? So that does satisfy all of these precedence relationships so far, okay? Now F has one predecessor, which is D. So I'm gonna draw F down here. And G has one predecessor, which is D. So let me draw G up here. And H has one predecessor, which is E. So I'm going to have H up here. I has one predecessor, which is A. So I'm going to have I. There is a predecessor A, right? And then finally, J has three predecessors, F, G, H. So we have F, G, and H here. Okay, then if I have J like this, and then we can extend this arc and then also this arc. Okay. Okay. Does that make sense? You got to be careful here. What's the problem here? In this network diagram, these two nodes are connected by how many arcs? These two nodes are connected by two different arcs, which is not okay, right? Because according to the construction rule, I believe rule number 3, the two nodes can be connected by at most one arc. So this network diagram violates the rule number 2, rule number 3, I believe. Okay, so in this case, we also need to introduce another dummy activity. So let me make a correction to that. So we have F, activity F down here, but after that, we're gonna have the dummy activity like this. So I'm gonna call it dummy activity 1 and then dummy activity 2 like that, okay? Also, the project is considered to be completed when all of the activities completed. So you make sure that the finish node is included in your network diagram. So I'm gonna include finish node here and then make a connection to here. Okay, so let me delete this. Okay, so I believe this diagram address all of the precedence relationship. Okay, so obviously, if you compare these two network diagram for this example, AON and AOA network, you can see that constructing the AON network is relatively easier than the one for the AOA network, right? However, our discussion in this class will be focused on the activity on ARC or AOA network model because its network structure is much more suitable for optimization, mathematical optimization formulations that you are going to discuss later. But it's not only for the CPM, but also for many other network optimization models, such as the shortest path problem, minimum spanning tree problems, and maximum flow problems, and so on. You just name a few. Okay, and most of these network optimization model, adapt the AOA network model. Okay, so let's talk about let's just focus on the AOA network model. or CPM in this class, okay? Okay, what's next? Oh, okay. And now let's label each event in this AOA network. So we can finish the AOA network diagram, okay? And we are going to use an algorithm for labeling events, okay? So the basic idea is that we label the event or the vertices on the project network so that the I is less than J if IJ is an activity. Okay, so that's the behind the logic on this algorithm. Okay, and for example, this is I, and this is J. Okay, and then we are talking about one of the activity, let's say A. Then we just make sure the number correspond to I is always less than the number corresponds to event number J. Okay. Okay. So okay. So we already labeled this node, right? And actually, this node has no predecessor, right? So it is labeled 0, like that. Okay. And then the ignoring node number 0. So ignoring this node has no predecessor, right? Ignoring this one has no predecessor. But this node has predecessor, which is this. This node has predecessor, which is this. Or this, right? And for this node, the predecessor would be this, right? For this node, the predecessor would be this node, right? So ignoring node number 0, we know that only this node has no predecessor. So it will be node number 1, okay? Now ignoring both nodes 0 and 1. Only this node has no predecessor, is that right? So it's gonna be number 2. So we need to do the same thing, ignoring 0, 1, 2. Actually, there are 2 nodes having no predecessor, right? This node has no predecessor, and this node has no predecessor. So if there is a tie like this, then you just need to arbitrarily choose one of them to be labeled number 3, okay? So this can be number 3 or this can be number 3, okay? Either this or this. So I'm gonna choose this just arbitrarily, okay? And labeled number 3 here. Now ignoring node number 0, 1, 2, 3. Again, there are 2 nodes without predecessors, right? This one has no predecessor and this one has no predecessor. So we will choose again one of them just arbitrarily to become number 4, okay? So I'm gonna just choose this arbitrarily, number 4. And then you just need to do the same thing, okay? And then this can be number 5 or 6, 7, and 8, for example, like this, okay? So I believe this is the exactly same network diagram, okay? Okay, so now using this network diagram, the AOA network, let's determine the critical path using the critical path method that we discussed, okay? So so as before, I'm going to use this notation. So for each activity, I'm going to put the name of each activity, and then I'm going to put the duration. Duration of each activity down here. And then I'm going to put the earliest start time, earliest finish time, latest finish time, and latest start time. Okay, for each activity, I'm going to use this notation. Also, for each event, for each node in the network diagram, I'm going to put earliest time and the latest time, okay, like this. So for each event, I'm going to have 2 squares. Okay, and then let me put the duration down here. So it's going to be 5, right? And B is 3, C is 3, but D is 2, E is 4, F is 4, right? And G is 2, H 8. Oh, what did I do? Okay. H is 8, I is 5, and J is 3. Okay, like this. Okay, so let's start computing the earliest time first. Okay, so I'm going to use different color. So I'm going to use green for the earliest time. So I'm going to use green. So starting at time t equals 0, the earliest time for the start node becomes 0, right? So we're going to have 0. So the earliest start time for both activities, A and C, becomes 0, right? So we have earliest start time for activity A and activity C's become 0, like that. And earliest finish time for activity A is going to be 5, right? Because it's only start time, which is 0, plus its duration, which is 5. So 0 plus 5 becomes 5 down here, right? So similarly, the earliest finish time for activity C is going to be 3, right? 0 plus 3 becomes 3, all right? And from the earliest finish time for activity A, which is 5, so the event number 1, for event number 1, the earliest time is going to be 5, because event number 1 represents the completion of activity A. Is that right? So which is going to be 5. Okay. So similarly, the early start time for activity B is going to be 5. Earliest finish time is going to be 5 plus 3, which is 8. Okay. Again, the event number 2 represents the completion of activity B. So the earliest start time for event number 2 is going to be 8 from here. Okay. So it's going to be 8. And we have dummy activity 1 up here. And the duration for dummy activity is always equal to 0, right? So likewise, later we're going to have dummy activity number 2. And the time duration for dummy activity number 2 is going to be 0 as well. Okay. So here, the early start time for dummy activity 1 is going to be 8 from here. And then early finish time would be 8 again, right? 8 plus 0 is going to be 8. Now we need to determine the earliest time for event number 3, right? And because event number 3 represents the completion of both activities, activity C and activity D1, dummy activity, right? So what you need is just take the largest value between these two, 3 and 8, right? So we're going to have 8 up here. Right? You remember that, right? So activity, in this case, E must be, yeah, I'm sorry, the activity C and dummy activity 1 must be completed before activity E can begin. That's why we take the larger value between these two numbers, right? 3 and 8. That's why we take 8. Okay, so 8 is going to be the earliest time for event number 3. Okay. Okay, so up here, early start time for the activity E is going to be 8. 8 plus 4 going to be 12, right? And down here we have 12, and then again 12 plus 8 going to be 20, right? And now we can also do this. The earliest start time for activity D is going to be 8, right? Copy it from here, 8. 8 plus 2, 10. So we have 10 up here. And then 10, 10, right? It's just copy from here. 10 plus 4, 14. 10 plus 2, 12, right? So down here we have 14, right? And then here we have 14. 14 plus 0 would be 14. Okay. And down here, the earliest start time for activity I is going to be 5, right? 5 plus 5 becomes 10. Is that right? It's very simple and straightforward, right? Now it's time for us to determine the earliest time for event number 7. And this time, again, we need to take the maximum value, largest value among these three, 20, 12, 14. All right? Because node number 7, event number 7 represents the completion of all these three activities, activity H, activity G, and the dummy activity, second dummy activity, right? So that's why you need to take the largest value, which is 20, okay? So the early start time for event, the early start time for activity J is gonna be 20, right? From here, 20 plus 3 is gonna be 23, right? Again, it's time for us to determine the earliest time for event number 8. So we need to take the maximum value between these two numbers, right? 23 and 10. So we are going to have 23, okay? So we have 23 down here, okay? Okay, now we can work on computing the latest time for this project. Since we know the project can be completed in 23 days, right? 23 days down here, right? So we know the latest time for event number 8 going to be 23, okay? So I'm gonna use blue this time. So we are going to have 23, okay? Let me 23. This is better. Okay, 23. So the latest time for the event number 8 is going to be 23. Now we can begin with the backward computation, right? Starting from event number 8 all the way to the event number 0. Okay. So the latest finish time for activities J and I becomes 23. So we have 23 and 23. Okay. And 23 minus 3, the duration for activity J is going to be 20. Likewise, 23 minus 5 becomes 18. So the latest start time for activity I is going to be 18. But the earliest, sorry, keep saying the earliest, but the latest start time for activity J is going to be 20. because the latest start time for activity J is 20, the latest time for event number 7 going to be 20. Okay. And the latest finish time for activity H is going to be 20 as well. And the latest finish time for activity G is going to be 20 as well. And the latest finish time for the dummy activity number 2 is going to be 20. Okay, which is all copied from down here. Okay, 20 minus 0 be 20, right? 20 minus 2 is 18. 20 minus 8 is 12. Okay. And the latest time for event number 6 gonna be 20, right? So the latest finish time for event for activity F gonna be 20 as well. 20 minus 4, 16, right? And up here, the latest time for event number 5 gonna be 12. Right? And then the latest finish time for activity E gonna be 12 from here, right? 12 minus 4, 8, right? And then latest time for event number 3 it's gonna be 8 as well from here. Likewise, the latest time for event number 4 is going to be what? We need to determine, actually, we need to determine the latest time for event number 4. And this time, we are going to take the smaller value between these two numbers, number 16 and number 18, right? So that's going to be 16. Then we have 16 as the latest finish time for activity D. 16 minus 2, which is 14, becomes the latest start time for activity D, right? And since we have latest time for event number 3 is 8, we're going to have 8 and 8 down here, right? 8 minus 0 is 8. 8 minus 3 is 5. Now we need to determine the latest time for event number 2. Again, we're going to go with the smaller value between these two numbers, 8 and 18. So it's going to be 8. And then we have latest finish time for activity B is going to be 8 from here. 8 minus 3, 5. So we have latest time for event number 1 is going to be 5. Okay. And then we have 5 minus 5 becomes 0, right? Now, again, we need to determine the latest time for event number 0. And we're going to choose the smaller value between these two, right? 0 and 5. So the latest time for the start node, node number 0, is going to be 0. Okay. Okay, now we computed the latest time and the earliest time for every event. And so now we can determine the critical path So in order to do that, we need to use the concept of a float, the total float, right? So if you remember, any activity with a total float of zero values, zero amount, becomes a critical activity, right? So I'm gonna change the color. I'm gonna use, okay, purple color. So you can just compare these two numbers or these two numbers. The difference between the earliest start time and latest start time for each activities, or you can just compare these two numbers, earliest time and the latest time for each event, okay? It's up to you, it's same. You're gonna end up with the same conclusion, okay? So since there is a difference of positive value of 5, which means the corresponding activity cannot be the critical activity. So C cannot be the critical activity, okay? But if you look at this, activity A, there is no difference between these two numbers, right? Which means the activity A will be part of the critical path, okay? Because it's gonna be the critical activity. The same for activity B, there is no differences between these two numbers, right? Which means B is gonna be another critical activity. And this dummy activity can be included in the critical path. And activity E can be included in H and J because of that reason, okay? So E, H, J. So these are the critical path, actually. You remember path from the start node, which is node number 0, to finish node, in our case, node number 8, that consists entirely of critical activities. Says this, right? It's called a critical path. So these are the, this is the critical path. Okay, so this is the critical path. And those are the critical activities. You don't need to include dummy activity because, you know, we artificially included, right? So it doesn't necessary to be included in the critical path. Okay, so this is our final answer. We can say that this the entire project can be completed within 23 days. And the critical activities does include activity A, B, E, H, and J, and these are the critical paths. Okay. Okay, so now let's take another example. So again, we are given with a list of activities and their description and the immediate predecessors, the duration of each activities. Okay, and so let's construct the AOA network activity on arc network diagram. Let me copy this table and put them in here. Okay, so I'm gonna move up here. Okay. Still, I need to move a little bit. Okay. Okay, so as usual, we start with, okay, what did I do? Okay, as usual, we start with node number 0, right? So we have node number 0. And because activity A is the only one, there is no predecessor. So we have, say, activity A. And the duration for activity A is 3. So I'm going to put them in here. And then I'm going to have activity B up here. And let's say I have activity C. And D as predecessor, which is C. So I'm going to have D. How about E? E has immediate predecessor, which is A. So I'm gonna have E down here. How about F? F has predecessor, which is B. So I'm gonna have F up here. How about G? G has predecessor, which is C. So we have, let's have F up here. How about, no, is that G? Right. So that's going to be G. And H has predecessor, which is C. Seriously? Okay. So H, okay, and then I has 2 predecessor. Okay. So, okay, here's what I'm going to do. So this is going to be H, right? And then I'm going to have I somewhere down here. In a way, I has 2 predecessors, F and H, which is true in our network diagram. And J has one predecessor, which is I. Okay. So I'm going to have J down here. Is that all? Okay. So I'm going to extend this arrow to here. What did I do? And then both activities, G and D, has to go all the way down here, right? So it's gonna go here and here as well. Okay. But here's, we have a problem because if you are looking at these two nodes, okay, these two nodes are connected by these two different arcs. So that's the violation of rule number 3 again, right? So what you need is to introduce the dummy activity. So instead of having, let's say, G there, I'm going to have dummy activity from here to here. Okay. Then I believe there is no violation. Okay. So I believe this is the one, but we need to complete the network diagram by labeling each event. So again, ignoring both event number 0 and 1. These two nodes has no predecessors, right? So we can arbitrarily choose one. So I'm gonna go with this. This is gonna be our event number 2. And then either of these can be node number 3, right? So I'm gonna go with this number 3. And then either of these can be the event number 4. So I'm gonna go with this. And then this must be number 5, 6, and 7. Okay. So we complete the AOA network diagram here. Okay, so now let's compute the earliest time. Okay, so as before, I'm gonna have two squares for each event. And I forgot to put the duration on this network diagram. So let me do that. 2, 6, 2, 3, 3, 5, 1, and this is dummy 1. There's no time, right? And then I set 1.5. Okay, it's 1.5. J is 2. Okay. Now I'm going to get back to this. Okay. So again, we start from time t equals 0, the start node. So the early start time for activity A is going to be 0. And early finish time for activity A is going to be 3. 0 plus 3 becomes 3, right? And then the earliest time for event number 1 is going to be 3. This is from here, right? Because event number 1 represents the completion of activity A, right? It's going to be 3. And then we have 3, 3, 3, right? 3 plus 2, 5, 3 plus 6, 9, 3 plus 3, 6, right? And earliest time for event number 2 is going to be 9, right? From here. And earliest time for event number 3 is going to be 5, right? And earliest start time for activity F is going to be 5, right? And likewise, the early start time for activities H, G, and D. So all equal to 9. This is from here, right? 9 plus 1, sorry. 9 plus 1, 10. 9 plus 5, 14. 9 plus 2, 11, right? So here, the earliest time for event number 4 is going to be 14, right? So the earliest start time for dummy activity is going to be 14. Earliest finish time is going to be 14 as well, right? Now we need to determine the earliest time for event number 5. So, before that, we need to have earliest finish time for activity F. That's going to be 5 plus 3, 8, right? So the earliest time for event number 5 is going to be 10, because we need to choose the larger value between these two numbers, 8 and 10. So it's going to be 10, right? So we have 10 plus 1.5, 11.5. And we have 11.5. And we have 11.5, right? Plus 2, 13.5. Is that right? What else? Did I miss anything? Okay, no, I didn't. So now it's time for us to determine the earliest time for the event number 7. So what you need is choose the largest value among these 4 different values, right? 13.5, 14, 11, and 6. So it's gotta be 14. So we determined the earliest time for every event, right? Since we know this project can be completed in 14 hours or 14 days, whatever the unit. So we know that the latest time for event number 7 is going to be 14. Okay, so I'm gonna use different color. So I have 14 down here. Now we're gonna do the backward computation. So here we have 14, 14, 14, and 14, right? 14 minus 3 is 11. 14 minus 2, 12. 14 minus 0, 14. 14 minus 2, 12. Okay. So we have 12 here, and 12 minus 1.5, 10.5, right? And then we have 10.5 here, and 10.5, 10.5, all right? And we have 14, this is from here, right? And then 14 minus 5, 9, right? And 10.5 minus 1, 9.5. 10.5 minus 3, 7.5, right? So we have 7.5, 7.5 minus 2, 5.5. Okay. Did I miss anything? No. Okay, now we need to determine the latest time for event number 2. Okay. What you need is to choose the smallest value among these 3, 9.5, 9, and 12, which is 9. Right? And then goes to here, 9 minus 6, 3, right? Again, we need to determine the latest time for event number 1. That's going to be the minimum value among these 3, right? That's going to be 3. 3 minus 3, 0, and then 0. Okay. Okay, now we obtained the latest time for each event as well. Okay. So next is to compute the total float to see where we have the critical path. Okay. So I'm going to use black color, okay, to mark the critical path. So starting from node number 0, event number 0, this is going to be our part of critical path because there is no difference between these two numbers, right? And then this is going to be the critical path, and this one, and this one. So the critical path would be A, or sorry, it's going to be 0, 1, 2, 4, 7. And the critical activities going to be A, C, G, right? That's it, ACG, and dummy activity. So you don't need to include it, okay? And we know that the project can be completed within 14 days or 14 hours, okay? Okay, I have actually one more example, but I'm gonna stop here for today, and then I'm gonna do this next time, okay? Okay, okay, thank you. I will see you next time. Bye-bye.